All right, welcome back. We are jumping right in today because this explainer is focused on a world that just completely defies all expectations. We're heading out to Jupiter's innermost Galilean moon, Io. And honestly, it's arguably the most extraordinary, chaotic, and just flat out fascinating celestial body we've ever discovered. But before we get into the nuts and bolts of how this moon actually works, let me throw a quick question your way. What is the most geologically active world in our entire solar system? Now, if you instinctively thought of Earth, with all of our earthquakes and volcanic eruptions, you'd actually be off the mark. The answer is a moon orbiting a gas giant. The answer is a staggering 400. That's right. Io has over 400 active volcanoes that are just relentlessly, continuously erupting and completely reshaping its surface as we speak. It is a world that is quite literally turning itself inside out. Okay, Section 1. The solar system's most volcanic. Let's set the stage here. Just take a look at this global map. Notice that incredibly colorful, deeply scarred surface? It's painted in these vivid shades of yellow, red, white, and black, all from sulfur deposits. And when we say it's volcanically active, we are definitely not talking about some gentle trickle of lava. Io features active lava flows that are up to 400 kilometers long. When its volcanoes erupt, they produce these massive umbrella-shaped plumes that blast sulfur and sulfur dioxide up to 500 kilometers straight up into space. I mean, we're talking about a literal simmering hellscape. Moving on to Section 2, a history of discovery. So, how did we go from viewing Io as just a tiny pinprick of light to understanding it as this massive volcanic engine? Well, it evolved over centuries. Back in 1610, Galileo Galilei used his newly improved telescope and spotted Io alongside Jupiter's other large moons. This was absolutely massive at the time because it proved that celestial bodies orbit planets other than Earth, which totally cemented the heliocentric model. Fast forward to the 1970s, the Pioneer 10 and 11 spacecraft flew by and detected a thin atmosphere and some really intense radiation. But the real shock? That came in 1979, when the Voyager 1 and 2 probes flew past and actually caught active volcanic plumes on camera. No one expected that. And since 1995, missions like Galileo and the currently operating Juno spacecraft have been getting incredibly close to study its deeply mysterious interior. Oh, and just a quick historical footnote for you. While Galileo originally wanted to use a numerical naming system, he was going to call it Jupiter I, it was actually astronomer Simon Marius who suggested the name Io. In Greek mythology, Io was a priestess of Hera and one of the lovers of Zeus. And since Jupiter is the Roman equivalent of Zeus, the name just stuck perfectly. All right, Section 3, the gravitational tug-of-war. So what is the engine driving all this absolute chaos? Well, Io is locked in a perfectly choreographed celestial dance called a Laplace resonance with two of Jupiter's other moons, Europa and Ganymede. It works like this. For every one orbit Ganymede makes around Jupiter, Europa makes exactly 2, and Io completes exactly 4. Because they periodically line up like clockwork, Europa and Ganymede repeatedly pull on Io's orbit from the outside, while Jupiter's massive gravity pulls it from the inside. This constant tug-of-war forces Io into a highly eccentric oval-shaped orbit. And that eccentric orbit causes something called tidal heating. Because Io's distance from Jupiter is constantly changing, the gravitational pull it experiences is constantly changing too. So here's the crucial point. Jupiter's gravity literally stretches and squeezes Io's solid surface. The solid ground of the moon flexes up and down by as much as 100 meters. Imagine the ground beneath your feet right now rising the height of a 30-story building, and then dropping back down every few days. That relentless flexing grinds the rock and Io's interior together, which generates an unbelievable amount of frictional heat. Exactly how much heat? Try 60 to 80 trillion watts of internal power. Yeah, trillion with a T. Because of this extreme tidal friction, Io's heat flow is more than 20 times greater than Earth's. It has so much internal heat built up that it simply has to vent it out, which is exactly why the surface is just riddled with hundreds of hyperactive volcanoes. Section 4. Sulfur, silicates, and plumes. Let's transition from the engine to the exhaust. We know why it's erupting, but what exactly is coming out of those vents? If we compare Io's volcanoes to Earth's, the differences are just staggering. Earth's volcanic eruptions typically eject material at around 0.1 kilometers per second, mostly releasing water vapor and carbon dioxide. But Io's eruptions, they are literally ballistic. They launch material at 0.5 to a blistering 1.2 kilometers per second. And instead of our typical lavas and water vapor, Io is spewing low-viscosity sulfur, sulfur dioxide, and ultra-hot silicate rock way out into space. Because of this totally unique chemistry, Io is a world of incredible extremes. For instance, despite being constantly smoothed over by lava, the compression of its crust creates mountains that dwarf anything on Earth. We're talking peaks reaching up to 17.5 kilometers high. That's double the height of Mount Everest. Beneath a surface frosted with sulfur and sulfur dioxide, it's got a silicate rock crust and a molten iron core. And all those vivid colors we talked about earlier, that's a direct result of sulfur compounds sitting at varying temperatures, painting the entire landscape in striking yellows, bright reds, whites, blacks, and greens. But what does the inside actually look like? Well, for a long time, scientists debated if Io's interior was just one giant, sloshing subsurface ocean of magma. Actually, scratch that. Recent data from the Juno spacecraft's gravity measurements gave us a major breakthrough. It turns out Io actually has a mostly solid mantle. So despite all that intense tidal heating, it's not a global liquid magma ocean. The magma must be rising really rapidly through a solid, extremely hot rock mantle just to reach the surface. Which brings us to Section 5, powering Jupiter's auroras. You see, Io's chaotic nature doesn't just stay on Io. It dramatically impacts its entire neighborhood. Invisible to the naked eye, but absolutely vital to the whole system, Io orbits deep within Jupiter's incredibly powerful magnetic field. As Io's volcanoes erupt, they eject vast amounts of gases into space. These gases become ionized, meaning their atoms are stripped of electrons, and they form a massive, glowing, donut-shaped ring of radiation right around Jupiter, known as the Io plasma torus. And because of this interaction, Jupiter's massive magnetic forces are actively stripping away 1 ton of sulfur and oxygen material from Io's thin atmosphere every single second. Just think about that. 1 ton per second. This material feeds directly into the Jupiter system, creating an intensely hostile, highly radioactive environment. And here is where it gets truly electrifying. As Io cuts across Jupiter's magnetic field lines, the moon itself acts like a giant electrical generator. It develops 400,000 volts of electricity across its diameter, creating an electrical current of 3 million amps. This massive current travels along Jupiter's magnetic field lines right down into Jupiter's atmosphere, triggering immense lightning storms and powering Jupiter's spectacular glowing auroras. Io is quite literally hardwired to Jupiter. It's mind-blowing. Section 6. A window to the past. So bringing all of this extreme science together, why does all of this matter to us down here on Earth? Well, studying Io isn't just about understanding a weird moon. It's about understanding the mechanics of the universe itself. Io acts as a natural laboratory for planetary evolution. Billions of years ago, shortly after they formed, the Earth and our moon were hot, partially molten, and incredibly volcanically active, very much like Io is right now. So by watching Io's heat and mass flow, we are essentially looking into a time machine at the youth of terrestrial planets. Furthermore, it helps us understand distant exoplanets and super-Earths where tidal heating might be happening right now, proving that strong tidal forces don't automatically mean a planet has a completely liquid magma ocean. Still, so many mysteries remain about exactly how this internal plumbing works, which is exactly why future missions are going to keep probing its depths. Which leaves us with this final provocative thought. As spacecraft like Juno continue to brave those deadly radiation belts to photograph Io's endlessly erupting surface, we have to ask, could this bizarre, sulfur-coated, constantly exploding moon actually hold the key to understanding how our own home planet cooled, stabilized, and evolved to support life? It just goes to show, sometimes you have to look at the absolute most hostile place in the solar system to understand the very ground beneath your feet. Thanks so much for joining me on this explainer, and I'll see you next time.